We've talked about roll stability, and we're now going to talk about roll control, and more generally, how that fits into the broader question of lateral control derivatives. Okay, so for roll control, we use control surfaces called ailerons. So if we look at a top-down view of the swing, and there's our center line, these are the control surfaces that sit out near the wing tips. And the reason we do that is those are placed out there to increase the moment arm, so that as you deflect the aileron, you get more a larger moment arm for that difference in lift between the two sides. So ailerons are deflected asymmetrically. So meaning that when one goes up, the other goes down in general. Now, they don't have to be exactly anti-symmetric. Anti-symmetric means that the right one would deflect down the exact same amount that the left one deflects up. That's not necessarily the case. So sometimes those are scheduled differently so that one will deflect more than the other for different reasons. And we won't really get into that, but just in general, understand that one will go down and one will go up. So if we look at the airplane from the back here, so this is the tail, and then we've got the main wing here. Then the right aileron, a positive deflection, is with the right aileron deflected down and the left aileron deflected up. Okay, so this is what we call a positive aileron deflection. And in general, what happens is the difference in lift that we get is increased on the right-hand side then for a positive aileron deflection, and delta L is decreased over here on the left-hand side. And so a positive aileron deflection corresponds to a negative rolling moment. Okay, so that creates a rolling moment to the left with a positive aileron deflection. So how could we predict the amount of rolling moment that we're going to get for a certain amount of aileron deflection and wing design? So one of the simplest theories is what's called strip theory. And in this theory, basically what happens is we use the section flap effectiveness. So, and this you could get from thin airfoil theory, for example. Basically, what that gives you is if you were to look at just the two-dimensional airfoil section, right? So if we just sliced this wing here and looked at the 2D airfoil section, then what we get from the section flap effectiveness is basically a change in lift, in section lift, as a function of aileron deflection. Okay, and so what we would do is we would assume, and I'll just draw another view of this wing here. So looking from the left, looking from the back, if we have a positive deflection, that's the right down and the left up. So basically, what we would say is if this was our original flap deflection, original lift distribution, then that lift distribution would be offset by an increase over here due to that aileron deflection, and a decrease over here due to the aileron deflection on the left-hand side. And then all we would need to do is integrate that difference in lift. So the rolling moment, so what happens is we estimate that the rolling moment is the integral of the delta L that we get across the wing. So on the right hand side it's positive, on the left hand side it would be negative for positive deflection. Multiply that by our coordinate, we'll say y, so the distance it is from the center of the aircraft, and then integrate in dy, and that would give us some estimate for the rolling moment caused by, and this would be a section lift here, but anyway, that would give us some estimate for the rolling moment caused by this deflection. Well, it turns out that this method is not very accurate. So strip theory turns out to be not very accurate, and that's because what actually happens, and I'll put this in red here, is actually we get some what I'm going to call spillage of dynamic pressure. So actually the lift starts to increase outboard of this, and 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 decrease something like this. So what we get on the left hand side is we get a decrease in lift. Anyway, something like that. It's a bit more smooth than what strip theory would predict, and actually that can cause some significant differences in what we predict for the rolling moment. So the best way to predict this really is to use a numerical method. This can be predicted by numerical lifting line algorithm, or from a panel code, or from CFD. All of those will capture this, and you can kind of understand what's happening here because we have a really low pressure. For example, for this positive deflection here on the right, what we're doing is increasing the lift, meaning that we decrease the pressure on the upper surface of the wing right in this region. But some of that decrease in pressure, that's a lower pressure now than the neighboring pressure here, and so we're going to get some spillage between the two. And so the low pressure here isn't going to be quite as low as strip theory would have predicted, because it's going to be affected by the higher pressure out here, and the pressure out here is not going to be as high as strip theory would have predicted, where it's actually going to be a little bit lower here. So that's basically what's causing this this spillage, and also that kind of, it smooths out our lift distribution, and predicts a difference in vortex shedding as well. And vortex shedding is important. We'll talk about in just a second here. But basically, this is a smoother transition than what would be predicted by strip theory. Okay, so let's look at a top-down view of the wing. So here's my wing here, and here's a fuselage and my horizontal stabilizer. And okay, let's talk about what happens now, or why we would deflect this aileron. Of course, we use it to trim out the aircraft, and we'll actually study that in a following lecture in a bit more detail, how to trim using this. But usually what we're using those ailerons for is to roll the aircraft, right? We want to roll the aircraft, and a lot of times the reason we want to roll it is because we want to turn. So let's say that we're flying along and we want to turn to the right. Okay, so what we'd like to do is bank to the right, and so not only roll to the right, but we'd also like to yaw to the right to get the aircraft to move in this in the direction here to the right. So what we would do is we'd actually give it negative aileron deflection. I'm going to draw this like this. So this is a negative aileron deflection, meaning that the right aileron actually comes up, the left aileron goes down. So that makes the delta L on the right hand side is going to decrease. The delta L on the left hand side increases, and that gives us a positive rolling moment. So so about the roll axis here, this gives us a positive rolling moment. All right, so we've banked to the right, but the challenge here is that this has also affected our drag on each side. So it turns out that with the decrease in lift on the right hand side, we've also decreased the drag most of the time. Okay, we'll talk about some exceptions here in a minute, but on most aircraft, you also decrease the drag on that side, and you end up increasing the drag on the left hand side by the increase in lift over there. And so what happens if we look at the let's say that's the center of gravity here, what happens is that we also create a yawing moment in this direction here. That's actually a negative yawing moment. Okay, so we've created a positive rolling moment. We've banked the aircraft to the right, but the nose of the aircraft actually wants to yaw to the left. This phenomenon is called adverse yaw, and it is present on nearly every aircraft in operation today. Most airplanes have this challenge just by the design of their wings and the aileron systems that when they try to bank the aircraft to the right, it wants to yaw to the left, and or if they wanted to bank to the left, it wants to yaw to the right. So this is a challenge, very common. So we call that adverse yaw. So what we usually have to do is to schedule the rudder deflection back here to overcome that adverse yawing moment, to create a yawing moment in the direction that we actually want the nose of the aircraft to go. So that's how we do it. So we have to now schedule the ailerons with the rudder if we want to turn this aircraft, to the right or to the left. It takes a coordinated effort between the ailerons and rudder. Now, I said there are some exceptions to this. To my knowledge, the first people that looked at this were the Horton brothers. The Horton brothers. And they looked at flying wings, and on a flying wing, you don't have a rudder to counteract this adverse yaw challenge, and so they looked at what they could do with the lift distribution on the main wing so they wouldn't have this adverse yaw. And there other people have looked at this too. There's a guy named Carl Nickel. I believe he did some stuff with it. He was a German mathematician, but also a pilot, and or I'm not sure if he was a pilot, but he studied flying wing aircraft, and then more recently a guy named Albion Bowers at NASA, who recently retired, and then our own lab here has also looked into this in quite a bit of detail. But what happens is so most aircraft are using something close to an elliptic lift distribution, and if that's the case, then it doesn't matter how you design these ailerons, you are always going to get adverse yaw. But there's another lift distribution that was produced or published by Prandtl in 1933 that's called a bell-shaped lift distribution. And this bell-shaped lift distribution has some advantages. We're not going to go into that in detail right now. But one of the interesting things about this is if you use this lift distribution, and there are others like it. So it's not just the Bell lift distribution. There's actually an infinite number of lift distributions other than the elliptic lift distribution that could be used to do this. But if you design your ailerons just right with these other lift distributions, you can actually get proverse yaw instead of adverse yaw. So this has been a really interesting area of study. And it's theorized, especially by Al Bowers at NASA, that this is the lift distribution used by birds because they use very little tail deflection in order to control yaw. So anyway, interesting ideas. But anyway, this is the concept of adverse yaw, and most aircraft, again, that are in flight today in operation experience adverse yaw. So this is something that's very common. Okay, so let's look at these results now in terms of terms of lateral control derivatives. Okay, so if we look at just the aileron, what we've learned today is that the reason we have an aileron is because we want to get a change in rolling moment. So we call that CL comma delta A. That's my change in rolling moment with respect to aileron deflection. But we also found that by doing that, we get a change in yawing moment for that same aileron deflection. The rudder, when we deflect the rudder, the reason we're doing that is to get a CN comma DR. We usually are deflecting the rudder to control the yawing moment, but the rudder actually can also create a rolling moment. So that is going to, we're also going to have a change in rolling moment due to rudder deflection. We can talk about that just briefly here over on the right. So if we look at from the back of the aircraft towards the front, and we deflect the rudder here, this is a vertical tail surface, so we deflect the rudder, what's going to happen is we're going to get this this change in lift on the one side here. And so usually that rudder sits above the center of gravity of the aircraft, And so that's going to create a rolling moment, right? So we can draw that rolling moment here. So that's what this is here. That's creating a rolling moment with respect to delta r. Now, that's from the vertical surface. We also, just like in side slip, we're going to have some interaction with the horizontal stabilizer. So that low pressure on the right-hand side here will actually create a low pressure and a high pressure on the vertical stable or on the horizontal stabilizer, and so we'll actually also get some rolling moment simply due to that difference in pressure on the two sides of the horizontal stabilizer. So these interactions again are fairly complex, and I would suggest using a numerical lifting line tool or a vortex panel tool or something like that to predict these types of derivatives or the change in rolling moment with respect to rudder deflection. But Phillips does have some estimates that you can use if, it's just an initial estimate. So the change in rolling moment with respect to delta R due to the vertical, he says you can estimate that from the vertical tail efficiency times SV HV over SWBW times epsilon R and times the lift slope CL, the vertical comma alpha, okay? And actually, he says that this would increase by 25 to 35%. So I'll just put a plus 25 to 35% if that vertical tail is also hooked then to a horizontal tail that's acting as like this winglet and would increase the lift slope basically of the vertical. Now, you also have an effect from the horizontal. So CL delta R on the horizontal tail. And what he gives for that is that you can use as an estimate plus or minus 0.08 times the vertical tail efficiency times SV BH over SW BW times epsilon R CLV alpha. And so we've got a plus or a minus here. You would use a minus if you're using a conventional tail, and you'd use a plus if you're using a T-tail. Okay, so anyway, that's what the plus minus there refers to. Okay, so we would basically add these two together in order to estimate this term right there. That's the total change in rolling moment with respect to rudder deflection. You'll have some influence from the vertical, some influence from the horizontal. Now, these two right here are what we call coupling terms. So the terms on the left here, these are our primary control surfaces that we're saying we want to use these for roll and yaw. So for roll, we want to use the aileron. For yaw, we want to use the rudder. But unfortunately, whenever we deflect the aileron, we also get a yawing moment. And unfortunately, when we deflect the rudder, we also get a rolling moment. So these two terms here are what we would call coupling terms. And we need to account for those because those are very present on most aircraft. And so we're going to find that we're going to need to balance all of these terms, not only our primary control moments, but also these coupling moments in order to trim the aircraft. Now, one last thing is that a deflection in aileron or rudder also changes our side force coefficient. So we're also going to have a CY comma delta A and a CY comma delta R. Okay, so these two are also going to happen most of the time whenever we deflect the aileron or the rudder. We're also going to get a side force component. Now, all of these derivatives together, let's put a box around all of this. These are called our lateral control derivatives. And we've talked about ways to estimate some of them. Of course, using CFD or these numerical panel codes or other low fidelity methods can also be used to estimate these. And they're actually usually fairly accurate below stall or for small deflections. That these lower order tools can be used to get pretty good estimates for these control derivatives. So in the next videos, now we're going to talk about how do we use these general control derivatives and also our stability derivatives to trim out an aircraft laterally.